Hello everyone and welcome back to this channel. In today's video, I'm going to show you how to solve this problem. This is a problem on work, energy and hour, but this problem in particular focuses on the calculation of work and also how to use Newton's second law to determine the coefficient of friction between two surfaces. All right, let's look at the problem. So a horizontal force of 150 newtons is used to push a 40.0 kilogram packaging crate a distance of 6.00 meters on a rough horizontal surface. If the crate moves at a constant speed, we are to determine the work done by the 150 Newton force, and also we are to determine the coefficient of friction between the crate and the surface. Let's look at the solution. The first approach to solving this problem is to identify your coordinate system. So the coordinate system is important because it helps us to track the directions and also the forces acting on these objects. So the coordinate system in this problem is going to be the Cartesian coordinate system, simply the XY coordinate system. So I'll have my vertical axis with the positive Y pointing upwards and then the negative Y pointing downwards. So in this case, any force pointing upwards is going to be positive and pointing downwards is going to be negative. In the same sense, I will have the horizontal axis along the X direction, which to the right would be positive and then to the left is going to be negative. With this, we can place our origin here. So we are going to place this packaging crate at the origin, and any forces that point to the right is going to be positive and then any forces to the left is going to be negative. In the same sense, forces upwards are positive, downwards are negative. Okay, now the next important step to take is to draw a free body diagram. A free body diagram is a simplified model where we represent the packaging crate as a point particle and then indicate all the forces acting on this packaging crate in their respective directions. So to do that, I'll first draw the packaging crate as a point particle, and then we know the first force we can think of acting on this object is the weight of the object, which point vertically downwards. All right, so we use an arrow to indicate the weight. So the weight is given as the mass of the packaging crate times acceleration of gravity, so mg. And then upwards we have a perpendicular force to those two surfaces, that is the bottom surface of the crate and also the floor. In that case, that force point upwards, which we call the normal force. Now to the problem. We have a horizontal force 150 newton which is pushing this 40.0 kilogram packaging crate. So I'll say, since it is horizontal, I'll take it pushing the crate to the right so that we have Fx to the right, and that is equal to 150 newtons. Also, we need to note from the problem that the surface is rough, indicating there is friction between the two surfaces in contact. In that case, we know friction is a force that opposes motion. So if the pushing force is to the right, then our friction force is going to point to the left, opposing this motion. So we represent the friction force with Fr. Now this is the free body diagram, and we can see we have all the forces acting on this object. All right, now we can apply Newton's second law for the vertical forces as well as the horizontal forces to solve this problem. All right, so let's look at the first part. We are to calculate the work done by the 150 Newton force. So in the problem, it is mentioned the crate moves at a constant speed. So if it's moved at a constant speed, then there is a condition that we need to take care of. So from kinematics, we know that if an object is moving at a constant speed, the acceleration of that object is zero. Okay, in dynamics, yes, if an object is moving at a constant speed, then the net force acting on that object is zero. So that is the condition here. So we are told the speed, which is the velocity, is constant. and that implies that the acceleration is equal to 0. Now, with this, we can solve this problem step by step. So let's first look at the work done by this horizontal force. So in physics, work is said to be done when an applied force moves an object through a distance in the direction of the force. The direction can be positive or negative x direction, or it can be positive or negative y direction. So with that, let's see how to solve that. So mathematically, we define work as the work done by a force is equal to the dot product of the applied force and the displacement. So we have the applied force, which is a vector, dot the displacement along the direction of the force, which is also a vector. Now let's do a quick review in mathematics. Anytime you take the dot product of two vectors, let's say vector A dot product vector B, then we have the magnitude of vector A multiplying the magnitude of vector B times the cosine of the angle between these two vectors. So we are going to apply the same definition here because we are using two vectors that are multiplying using the dot product. So that is the definition for work. All right. So now in this case, we are going to have the work done equals the magnitude of the force. So F without that bar at the top times the magnitude of the displacement, which is distance, and then the cosine of the angle between the force and the displacement. So the angle theta. All right. However, we can see that the displacement is along the direction of the force. So we have it here as delta x, right? So that is 6.00 meters given from the problem. Now, the angle between this force and this displacement, we can see clearly is 0. So theta in this case is going to be 0. So we have the angle is equal to 0 and cosine of 0 is always 1. All right. This will give us the work done on the crate is equal to the magnitude of the force times the distance, which is the magnitude of the displacement, cosine of the angle between them, which is cosine of 0, but cosine of 0 is 1. Okay, so we have 1. Therefore, we have the work done to be nothing but the force times the distance. All right, now we can plug in the values to find the work done on this packaging crate. So the magnitude of that force is what? 150 newtons multiplying the distance, which is 6.00 newtons. So if we do 150 times 6, that will give us 900, and then we have the newton times meters. Okay, so that will give us newton meter. All right, but 1 newton meter is equal to 1 joule. So that is the unit for works. Therefore, we can say the work done is equal to, in standard form, 9.00 times 10 to the power 2 joules. So let's look at part B, where we are to find the coefficient of friction between the crate and the rough surface. All right, so to find the coefficient of friction, that is mu, we need to go back to Newton's second law. Okay, this time we are going to look at Newton's second law in both the horizontal and the vertical case, and we will see why. So first of all, we still keep our coordinate system. All right, we keep our coordinate system, and then we also have our free body diagram. Now, if we consider Newton's second law, which says that the sum of all the forces acting on the object is equal to the mass of the object times the net acceleration. In this case, for the horizontal case, we know that the Newton's law is going to be the F net in the horizontal direction should be equal to the mass times the horizontal acceleration. However, we know acceleration in this case is 0 because the crate was moved in a constant speed motion. Okay, so with that, the acceleration along the horizontal direction is 0. So the net force, I'll use the sum of all the forces along the horizontal direction is equal to 0. Now, what are the forces acting along the horizontal direction? We do have to the right, which is positive, the Fx applied, and then opposing that force is the friction force, and that is equal to 0. So we can see that the applied force is just equal to the friction force. That is why the object is moving at a constant speed, because the net force is not producing any net acceleration. So we have the friction force is equal to the Fx. But we have to remember that the friction force is nothing but the coefficient of friction times the normal force. How do we know the normal force? We need to do Newton's second law along the vertical direction, because the normal force is one of the vertical forces acting on this crate. So in the horizontal direction, we found out that the net force is equal to 0. In the vertical direction, however, the net force is also going to be 0, because in the vertical direction, there's no motion of this object. So there's no displacement along the vertical direction. Therefore, there's no net acceleration along the vertical direction. Therefore, we can say the sum of all the forces along the y direction is equal to 0. The object is, or the crate is not moving vertically. Now let's sum up all the forces acting on this crate vertically. So if you look at our coordinates, we can see that any force that point upwards is going to be positive, downwards is going to be negative. So upward we have the normal force itself, downward we have the weight, which is mg minus, and then that is equal to 0. So clearly we can see that the normal force is nothing but the weight mg. Now we can plug in the values. So we have the mass of the crate, all right, that is equal to 40.0 kilograms, and then times the acceleration of free fall, 9.8 meters per second squared. So multiplying this together should give us 392 newtons, and this is the value for the normal force. And we need this information to be able to determine the coefficient of friction between the surfaces. All right, so let's come back here to our equation. So friction force is the coefficient of friction times the normal force. So we can put that in here. So mu n, okay, in place of friction is equal to the applied horizontal force. So with that, we can see that we can calculate the mu by dividing both sides by the normal force to isolate mu, and then we are left with mu, which is the coefficient of friction, is equal to the applied force Fx divided by the normal force, which we just calculated here. Now let's plug them in. So the applied force was 100, or is 150 newtons, divided by the normal force, which is 392 newtons. Therefore, the coefficient of friction is calculated to be 0.38, and then we can see the 2 newtons here cancel out. So that makes this coefficient of friction a dimensionless constant, or unitless constant, and it is dependent on the nature of the surfaces in contact. Okay, all right, so this brings us to the end of this problem. And if you are new to this channel and this was very helpful to you, please don't forget to give us a like, share, and also subscribe to this channel. If you are already part of the community, thank you very much, and let's keep doing physics. Until then, I'll see you in my next video. Bye bye.